Bem-vindos ao nosso espaço, um mergulho profundo nos assuntos mais interessantes de esportes, ciências e temas gerais do momento. Aqui você vai encontrar conteúdo de qualidade, com análises empolgantes e descobertas fascinantes que vão expandir seus horizontes. Nossa missão é trazer informação relevante de forma dinâmica e descontraída. Queremos que você faça parte dessa jornada incrível de conhecimento e diversão. Se gostar do nosso conteúdo, não esqueça de deixar seu like e se inscrever no canal para não perder nenhuma novidade. Ative o sininho também. Aproveite!
If you love science, don't forget to like and subscribe. In 1948, a mathematician named Claude Shannon published a paper that would change the world forever. He introduced the concept of information theory, a framework for understanding how messages are sent, received, and distorted by noise. While we usually think of Shannon's work in the context of telecommunications, fiber optics, and the internet, his equations are quietly governing a much older system, the survival of life on Earth. This is the story of the Shannon camouflage, the realization that animal mimicry isn't just a biological fluke, but a sophisticated application of information processing. To understand this, we first have to look at what information actually is in a mathematical sense. In Shannon's world, information is the reduction of uncertainty. If you receive a message that is highly predictable, it contains very little information because you already knew what was coming. However, if a message is surprising or unexpected, it has high entropy. In the wild, a predator's brain acts as a biological receiver. It is constantly scanning the environment, trying to decode signals that indicate food or danger. Evolution, therefore, is an ongoing arms race between the sender, the prey, and the receiver, the predator. Think about a moth resting on the bark of a tree. To survive, the moth needs to become noise. In information theory, noise is random data that obscures a signal. By evolving wing patterns that mirror the high-entropy, chaotic textures of tree lichen, the moth effectively increases the signal-to-noise ratio of the environment to the point where its own message, the fact that it is a moth, becomes unreadable. The predator's neural decoder fails to isolate the object from the background because the visual data of the moth is indistinguishable from the statistical properties of the bark. This is the mathematical essence of crypsis, becoming part of the environmental entropy. But what happens when an animal doesn't want to hide, but wants to lie? This leads us to the phenomenon of mimicry. In Shannon's framework, this can be viewed as signal hijacking. Consider the hoverfly, a harmless insect that looks almost exactly like a stinging wasp. From an information standpoint, the wasp has spent millions of years establishing a high-priority, reliable signal of danger through its yellow and black stripes. This signal is so redundant and clear that it survives even in the noisy environment of a busy, wind-swept meadow. The hoverfly exploits this established communication channel by sending the same message. It uses a form of biological error correction code, where the visual pattern is so similar to the original wasp signal that the predator's brain automatically corrects any slight discrepancies, concluding with high confidence that the fly is a wasp. The fly is essentially using a shortcut in the predator's data processing. Shannon also predicted that for a message to be effective, it must be transmitted over a specific channel. In nature, that channel is the light reflecting off the animal and the atmosphere or water through which it travels. Researchers have found that animals often optimize their patterns based on the specific bandwidth of their habitat. For instance, fish in the deep ocean, where blue light dominates the channel, utilize different visual bits than those in shallow, turbulent reefs where light is scattered and chaotic. The complexity of an animal's pattern often correlates perfectly with the complexity of the background entropy. If an animal is too simple in a complex environment, it stands out as an ordered signal in a chaotic field. Conversely, if it is too complex in a simple environment, it becomes a conspicuous target. Natural selection acts as the filter that removes the bad data. The most fascinating part of the Shannon camouflage is how it explains the limits of evolution. Just as a computer file can only be compressed so much before losing vital data, an animal's camouflage can only be so effective before it becomes too biologically costly to produce or too specific to a single location. This is why we see generalist mimicry. Some animals evolve patterns that are good enough to confuse the predator's decoder across multiple different backgrounds. They are essentially using a lossy compression algorithm for their survival strategy, sacrificing perfect accuracy for broader utility. Recent studies in computational biology have begun using Shannon entropy to quantify exactly how well a creature blends into its surroundings. By measuring the information gain a predator receives when looking at a scene, scientists can predict which species are most likely to survive an encounter. We are finding that the most successful camouflaged animals are those whose skin textures perfectly match the statistical surprise or randomness of their natural habitats. The next time you see a chameleon change its color or a walking stick insect vanish into a branch, remember that you aren't just seeing a miracle of biology. You are seeing a living manifestation of information theory. Nature is a master cryptographer, constantly encoding and decoding the secrets of survival in a world filled with noise. For more incredible facts like this, don't forget to subscribe and turn on notifications.